Hello everyone, and welcome to our virtual summit presentation. We are Team GAPS-COMM, and we are sponsored by iXblue Defense Systems. On this project, we were given assistance from our technical directors Patrick Moran, Daniel Nugent, and Jeremy Peacock. The GAPS-COMM team consists of 2 computer engineers, myself, Cruz Marcel, and John Travis Hunter. The GAPS-COMM team also has 2 electrical engineers, Kyle Keefe and Ariana Angeloni. Before we begin talking about the project, here's a little background about the sponsoring company. iXblue Defense Systems is headquartered in France. The company specializes in design and manufacturing of advanced autonomous, marine, and photonics technologies. One important product used in this project is the GAPS device. GAPS stands for Global Acoustics Positioning System. To give a general overview, the GAPS device is used to track underwater vehicles that are within its range of operation. The goal of this project is to cooperatively join the ranges of multiple GAPS devices to track vehicles over a larger range. The motivation for this project was to enhance the GAPS transponder tracking over larger distances. To achieve this, the team would need to create software that is capable of managing the cooperative operation of multiple GAPS. A key motivation to the project is that there is a need for a modular, scalable acoustic positioning array within the market.
A major component of our project was the anticipated best outcome, or ABO. This includes all of our goals, which fall under 4 categories: user interaction, automation, network, and system output. For user interaction, our main goal was to be able to create a GUI similar to the picture on the right, where users would be able to enter certain properties that they wanted the system to use. For automation, we were looking to be able to handle multiple beacons between gaps, not just one gaps at a time, which would also include scheduling beacon interactions, so when a beacon would talk to each gaps. For network, we wanted to be able to send commands to each gap depending on user input and some other variables, which we will talk about later. And for system output, we just needed to be able to handle the flow of data. So our team was able to achieve our ABO, so let's take a look at our old system capabilities compared to our new system capabilities. With both systems, users were able to access a GUI and change system parameters. In the old system, they were able to manage one gaps at a time, but with our new system, they can connect multiple gaps together into a network and manage them that way. In the old system, beacons were only tracked when they were within one GAPS radius. With our new system, since the gaps are connected, we can track beacons as they move between gaps, which is we call the handover, which we can talk about later. Something the new system does that the old system could not is that our new system uses the beacon's current and predicted positions and plots them so that the user can see any possible invalid data points. So this is a summary of some technical accomplishments by the team over the course of the project. And it starts out with becoming familiar with the current working GAPS system for one GAPS, and then slowly progresses into designing, developing, and testing software that allows for a multi-GAPS system. Another detail here is the economic impact for the company overall is that this project helped reduce the time spent during beacon configuration and management, which we will detail later. But it also allows for large-scale beacon monitoring because of the GAPS network, which also actually expands the product use cases and reduces the manpower required during these operations. So our project actually followed this main cycle. So we started with project organization, planning out what we wanted to do and how we wanted to do it, and then subsequently documenting how we wanted the system to work. And then we moved on to developing the software, and from there we tested and noted our results. So that's the order that this presentation is going to go in as well. So to start, this is an overview of our project from its first stages. So here we can see that the control and data interface, or the GUI, connects to the control software, which is not a physical module, it's more of a software module. And then from there, it can contact separate GAPS and then tell them what the user wanted them to do. And then from there, it contacts the beacons at the very bottom and then awaits a response. And then from there, we can plot our data points and see how our system is working. So my name is Angie, and I'm going to go over some of the things that I worked on individually related to the project. So the first couple things that I did were related to documentation. As I said before, we designed our project before we actually wrote it, before we did any of the software development. So some of the documentation that I was a part of here is listed. The SRS are the software requirement specifications, so what we wanted our software to do. And then also our SDS, so the software design specifications, so more specifically flowcharts and things like that, as well as testing parameters, so suggestions for the company as to how they should test each software module and how it should respond. Hardware operations outlines the very basic connections between the GAPS and the Wi-Fi systems and things like that, which I believe I have here. I also took care to make sure that the documents were uniform, so there was no confusing language on any of them, just for traceability. I also took care of the Team Trello, which is our project management software, which looks like this, where we broke down our current objectives, our future objectives, and any completed tasks, which helped us with project management. Some other technical contributions of mine were testing the mesh network, which is the kind of like the internet that the GAPS network uses to communicate with each other. And then I also helped design the beacon handover, specifically the predictive positioning, which basically is this more or less confusing flowchart, which details how our beacon handover uses the various components of the software to be able to predict where the beacon is going, to see whether or not it needs to hand over, so whether or not it needs to communicate to a different GAPS, if or when it crosses from one GAPS into another GAPS area. I also helped design the GUI with the integrated 2D plotter, which we will see a bit later. And the next speaker is Kyle, so he will take it from here.
Thanks, Angie. My technical contributions to the project span from hardware setup to design, programming, and testing. Additionally, a major deliverable for iXblue was the inclusion of documentation specifying the program's requirements and design, and I, along with my teammates, made contributions to those documents as well. Firstly, this project's hardware-oriented work was fairly limited. The devices that we worked with were already fully operational commercial products, and our goal was to manage a group of them, meaning that our main hardware concern was that of communication between said devices. It would be severely limiting to operate a number of GAPS while maintaining a central wired connection to a computer, so a local wireless network across which the software could communicate with multiple devices stood out as a solution. I performed the setup of this network, designating a master router and connecting a secondary one set to simply copy its parameters and provide access to the network. As previously mentioned, Angie was later responsible for testing these connections to ensure that data and commands could be sent between network devices. Next, I participated in the design process of the two modules that our team coded entirely from scratch. Early stages of this design mostly involved the creation of software flowcharts that depicted the intended information flow of each module and broke down their roles into distinct tasks, which later became individual software functions on the development end. My main responsibility was the design of a module titled the Spatial Track, personally creating its flowchart, which saw several revisions during both the design and development stages. I secondarily contributed to the lower level of the two flowcharts created for the beacon handover module, specifically assisting in the design of the portion responsible for performing predictive math using data that the Spatial Track had been responsible for calculating. When it came to start developing the software modules, I coded the Spatial Track using Python, where it served to interpret data received from the GAPS after it had been passed through a parser and stored in a buffer. It kept track of beacon IDs, beginning calculations for each only when it had provided a certain number of data points, and sought to root out and mark data that appeared erroneous to prevent it from interfering with later processes. Avoiding data it deemed invalid, it then calculated the component velocities of each beacon to be used during handover. In order to calculate these velocities, it was necessary to convert positioning data in the form of latitude and longitude to a measurement of absolute distance between data points, and the function responsible for this was adapted so that it could be utilized again in the handover module. Finally, as I mentioned earlier, I contributed to documentation that served to promote readability all the way from the inception of our project's goals to their completion. As a brief explanation of these documents, the Software Requirements Specification, or SRS, outlines the main tasks that the project had to accomplish. It was the first major deliverable of the project and served to take goals specified by our technical director and split them into modules. If the SRS laid out a plan for exactly what our project was going to do, the Software Design Specification, or SDS, described how it was going to do so. The software flowcharts I described earlier went here, and other specifics included intended functions and specific methodology are also included in this document. It also served partly as a changelog for the code as it went through several iterations and received updates. Finally, the testing specifications document was smaller and really only served to describe how the module's prototypes would be tested. It also detailed problems encountered during testing and any results thereafter. Without further ado, I'd like to introduce Cameron Cruz Marcel, who will be speaking next.
Hello. My main role in the team was to help create modules of code and create the control and data interface. 3 main contributions I made to the team was coding for TCP communication, the creation of flowcharts, and the creation of software modules. The first important coding task that was accomplished was using a TCP connection to communicate wirelessly with the GAPS device. TCP connections are reliable and will not drop or corrupt packets. The user will input the GAPS IP addresses into the user interface that will be used in the connection. iXblue has been using a web-based interface to interact with and configure the GAPS device. The old connection between the user and the GAPS is seen on the right. The new setup allows for multiple clients to be connected on a local network. The setup on the left is what the team used to test the software on a real GAPS device. My computer was used as the server, and due to limited testing equipment, Kyle's computer was used to emulate a second GAPS device. The communication modules were tested and verified to be working properly across the local network. More specifically, data was properly ingested into the software and the GAPS was able to start and stop tracking via software commands. For the data parser and buffer, sample code provided by Patrick Moran was used to lead the development of these 2 modules. The data buffer is capable of storing several streams of data from GAPS devices. The parser then takes one string of data at a time and places the corresponding information into the correct columns to be used in further calculations. The indexing method had to be modified from a time-based index to a linearly increasing index as there were crucial bugs that could cause the program to fail. The beacon configuration module was not able to be fully tested and will need to be further modified. The main goal of this module was to configure the tracking parameters of a specific beacon. This would include things such as the frequency of tracking, the code used to interrogate the beacon, and the reply code the beacon would send back. The GAPS Graphical User Interface, or GUI, is a crucial part of making the software user-friendly. The user will put in the number of GAPS and beacons that will be used as well as the IP addresses of the respective GAPS devices. Additional inputs can be provided to improve the accuracy of the software. If no input is given, default values will be used. Once the GUI is up and running, the proper TCP connections will be automatically established. The Start button will begin the plotting of the GAPS and beacon positions. If a position is deemed invalid, then the point will be marked red. Otherwise, the valid point will be marked blue. As the software is running and a beacon handover occurs, all previous points are marked gray to allow for easy visualization of the handover. When the user is done, they can press the Stop button and all the GAPS devices will stop tracking and the GUI will wait for further input. The Save button will save the entire data frame into a time-stamped Excel file. And now I would like to introduce our next speaker, John Travis Hunter.
Hello, I'm John Travis Hunter. I'm studying computer engineering at URI, and I've been working on the software development for the GAPS-COMM Capstone project. Over this software development lifecycle, I've been working on the software documentation as well as flowcharts for each of the software modules. I programmed the beacon handover software module, which I'll go into detail later. I also programmed a positional test data generator to provide us with test data for testing in different scenarios to make sure our software works. And I've also focused on plotting how our data is processed as it goes throughout our entire software pipeline. This plot on the right here shows the positional data that was simulated based on real-life data. We generated a fake GAPS, which is in green up top. It's called GAPS 129. And then we have our beacon 1 position in the blue there on the bottom left. And that beacon just stays kind of stationary with a little bit of drifting. And then we have our GAPS 0, which is modeled after real-life data. And this GAPS is doing circles and spiraling away from the beacons. So GAPS 0 starts very close to the beacons, but over time it spirals away from the beacons, which eventually means that GAPS 129 will be closer to the beacons than GAPS 0. This is important to see because eventually GAPS 0 will be much farther away than GAPS 129, and the beacon 1 is going to have to belong to a GAPS. So using our software, we can calculate when we should hand the beacon over from GAPS 0 to GAPS 129. For my individual technical contributions, I programmed the beacon handover software module. This module predicts when to hand over a beacon between multiple GAPS. It also generates plots to demonstrate when and how the handover is calculated. Over the course of this software development cycle, we realized that we needed some more data sets for us to test our software on. So I created the test positional data generator, and this generates positional data for different situations that we can test our software on. This test data generator allows us to create different scenarios to test our software in. For example, if we need a scenario where there's 3 GAPS in the field and they are handing over 1 beacon between them, then we can generate data for each of these GAPS and the beacon itself and say where they are, what they're doing, how they're moving, and then we can use that to test our software and make sure that it works in all these different cases. I've also been contributing to the software design specification document, making sure that our software is readable, making sure that it's documented and understandable by the other engineers who need to use this. I've also provided debugging support on other software modules like the spatial track. I've been focused on giving feedback to the user of this software so they can see how the data comes into our software program, how it's processed by each of the modules, and how it impacts the GAPS and the beacons at the end of the software by telling the GAPS to hand over a beacon at the appropriate time. So the user of the software is going to be able to see everything that's happening and understand why it's happening and how it's happening. I also helped perform lab testing on our software using simulated data on a physical GAPS hardware device. To test this software, we started with the simulated data I discussed earlier. And you see here we have our positional data on the left. And so when it comes into the beacon handover, we calculate a distance ratio between the beacon and each GAPS. So we take the distance from the beacon to GAPS 0, and we take the distance from the beacon to GAPS 129. And we see which GAPS is closer, and using that ratio, we can decide when we should hand over the beacon from one GAPS to the other. On this graph on the right here, you can see we have annotated the handover at a certain time, and you can see that it hands over 3 times. And this handover corresponds to the positional graph on the left here. Because GAPS 0 is spiraling away from the beacons, you can see how this impacts the plot on the right. So initially, the beacon belongs to GAPS 0. But because GAPS 0 is spiraling away, you can see that GAPS 129, this purple square plot line here, it gets closer and further and closer and further until eventually GAPS 129 becomes closer for just a little bit of time. So the software performs a handover at that point, giving the beacon to GAPS 129 and taking it away from GAPS 0. But as you see, GAPS 0 spirals back a little bit. So we have this small portion where GAPS 0 is just a little bit closer. So we hand the beacon over for that small amount of time. But then GAPS 0 goes on its way, and the beacon belongs to GAPS 129 for the rest of this data set. This is how the beacon handover works. During lab testing, we use this simulated data set in conjunction with an actual GAPS hardware. So we had GAPS 0 be our simulated gaps, and GAPS 129 be representing our actual hardware gaps. And so initially, the beacon belongs to GAPS 0. But as it went into the range of GAPS 129 and the handover was performed, we could even hear the acoustic pinging of GAPS 129 in the lab. This proves that the core functionality of our software was operational. After proving the core functionality of our software, we were ready to provide our project deliverables to iXblue Defense System. This includes our graphical user interface with the settings menu, our software for our autonomous beacon tracking. This is tracking the position, speed, validity of the data, and most importantly, when to hand over a beacon from one GAPS to the other. We're also providing our software and hardware documentation for all the software modules and how the software works in general. And we're also providing the test data generator for generating more data sets for further testing of the edge cases of the software. Throughout this year, most of our development was performed remotely. We all worked together over Zoom and Discord, and we all developed experience working with GitHub and sharing our code remotely to each other and collaborating on this software project without being in the same area. We did do our live testing in the lab, and that was a really great experience to work with the actual hardware and make sure that our software works on the existing system. As a team, we would like to thank our technical directors Patrick Morin and Daniel Nugent. Our technical directors gave us all the help we could need and provided us with all the tools we needed to succeed, and met with us every week to discuss our project and make sure we were on track, and that was so helpful. We would also like to thank Capstone Program Director Dr. Sunak, who gave us this opportunity to have a real-world experience and connect with these industry leaders and develop ourselves as engineers. We would also like to thank Assisting Technical Director Jeremy Peacock for helping us throughout this process. This Capstone project has been a great opportunity for us, and we hope that you enjoyed our presentation. Thank you for watching.